All right, this example says the blood pressure represented by the variable P for a certain individual follows a pattern of simple harmonic motion during the pumping cycle between heartbeats. The minimum pressure is 80 mmHgs, and that stands for millimeters of mercury. And the maximum pressure is 120 millimeters of mercury. The individual's pulse is 60 beats per minute, and we need to write a model representing the blood pressure at a time t seconds into the cycle. And we're given some important information here. Assume that at t equals 0, the blood pressure is 100 millimeters of mercury and is initially increasing. So again, we're given a lot of information in here. And I'm going to start by drawing a picture just because that always helps me. All right, so here's what we know. We know the maximum blood pressure in this situation will be 120 millimeters of mercury, and we know the minimum will be 80 millimeters of mercury. But we know that when t is equal to 0, that the blood pressure is 100 millimeters of mercury and is initially increasing. So that means that we have to assume that this graph is going to start here and initially be increasing. And when it increases, it's going to increase to the maximum of 120. And then as it follows through, it will decrease to the minimum of 80, and then go back up and increase to the maximum of 120, and so on. So we have to assume that the graph of this particular situation will look something like this. One of the first things we're going to need to write this model is the amplitude. And we know that the amplitude is the distance from equilibrium to the top of a wave or to the bottom of a wave. Well, it appears from our drawing that we were given equilibrium. Equilibrium is at 100 because that's halfway between 80 and 120. So that means that the amplitude is the distance from 100 to 120 or from 80 to 100. So we know that our amplitude is 20. And as we just noted, we also know our equilibrium. And our equilibrium is going to be at y equals 100. And we know that when we find our equilibrium, we also have found our vertical shift. Now, to write this model, we're also going to need to know omega. And to find omega, we're going to have either the period or the frequency. Now, in our problem, we're told that the individual's pulse is 60 beats per minute. Well, that in and of itself is a frequency. The heart is beating frequently with it's beating 60 beats every minute. That is a frequency. But our time in this particular model that we're going to come up with, our time is in seconds. So we need our frequency to be in seconds as well. Well, if the pulse is 60 beats a minute, that's 1 beat per second, and that's our frequency. And we also know that the frequency, which in this case is 1, is equal to omega over 2 pi. Cross multiply, and we get 2 pi equals omega. So we just found our omega. So all of this is important information, but probably not the most important piece of information. The most important piece of information is we have to make a decision. Are we going to model this situation using sine or cosine? Well, as we look over here at our graph, we can see that when t is equal to 0, that we are at equilibrium because 100 mmHgs is equilibrium. And we know that anytime when we are at equilibrium, when t is equal to 0, we're going to use a sine function to model that. So we know we're going to use the sine function, but now we have to make a decision. Are we going to use the positive sine function or the negative sine function? Well, the fact that we were told that the blood pressure is initially increasing, in other words, it's initially going up, we know that that graph looks like the graph of the positive sine function. Had we been told that the pressure was initially decreasing, in other words, going down, then that would have been the graph of the inverted sine function or the negative sine function. But because we're told that we are initially increasing in this situation, we'll use the positive sine function. So putting all of this information together, we will have our model, and that model will be P, because it models the blood pressure, is equal to our vertical shift, which is 100, plus the amplitude times sine of 2 pi t.